All right, today we are talking about solutions and solubility and solution concentration units. So that's what we're doing today. So before we go any further, let's define a solution just so we all know what we're all talking about. A solution is really any homogeneous mixture, okay, we might say with particle sizes smaller than 2.0 millimeters. But I'll save that for another minute. Okay, so homogeneous mixture, and it can actually be solid, liquid, or gas, right? So you could have a homogeneous mixture that is a solid, that might be an alloy like brass or bronze, right? Where it looks like it's just all one metal, but it actually has, say, copper and tin or copper and zinc in it, right? It can be a liquid, which is what the rest of this chapter is going to be about, but a gas can also be a homogeneous mixture. Like the air you're breathing is a homogeneous mixture of nitrogen, oxygen, and argon gases. So that's what a solution is. For the rest of this chapter, we're going to focus just on liquid solutions. And for liquid solutions, we're going to add this little asterisk, right? We've got a homogeneous mixture with particle sizes smaller than 2 nanometers. Particle sizes smaller than 2 nanometers. And you might say, that's a weird, why that cutoff? Well, the reason is that if you're smaller than 2 nanometers, then the light can pass through it without scattering because you're smaller than the wavelength of the light. So the light just kind of rolls over you. But if you're bigger than 2 nanometers, then you're bigger than the wavelength of the light. And so instead of having the light pass through, it gets scattered and you start to become cloudy or opaque. So for example, Kool-Aid would be a solution because the light can pass through it, even if it changes color, the light passes through it. But milk technically is not a solution because the light gets scattered, right? So those larger particle sizes say, hey, you know what, actually, I know you look like a regular old homogeneous mixture, but under normal circumstances, you would actually separate you might separate into several layers, right? And so something with particle sizes larger than 2 nanometers would be a colloid or a suspension, okay? In a suspension, those larger particles are suspended and then they'll fall out. Like if you put dirt in a jar and you mix it up, it would actually stay suspended for a little while and be cloudy. That'd be a suspension. A colloidal suspension is one that stays suspended. And milk is a good example of a colloid. So that's just kind of a little background on how we're going to define these things. But we're not going to focus too much more on that. Really, our primary focus on this chapter, is going to be looking at solution concentrations. And so we just have a little bit of background here where we're kind of defining the space here, what solutions are. All right, so the other thing we need to talk about is kind of define some terms here. A solution is a mixture that contains the solute plus the solvent. And roughly speaking, the solute is the thing that is being dissolved, and the solvent is the thing that is doing the dissolving. So it might be, especially if one is in smaller quantities, it's easier to tell, right? So in our Kool-Aid example, the solute, the thing that was dissolved, includes sugar and the flavoring packet and the color. I guess there are multiple solutes here, right? Whereas the solvent in that Kool-Aid example was the water that was dissolving it, right? So this is the liquid doing the dissolving. Does that make sense? Okay. And in fact, gases can also dissolve into liquids, right? So oxygen can dissolve into water. That's how fish breathe, right? If there wasn't any oxygen in the water, then they couldn't breathe. So it could be a liquid solute, a solid solute, or a gas solute dissolving into our solvent, right? So we get kind of interesting different processes here. And when the two combine to form a solution, that process is called solvolysis. So actually I'm going to just rearrange this here, make it like a reaction almost. It's not a reaction because we're just making a mixture, right? As we just defined, we said this is a mixture, it is not a chemical reaction. But the process by which the solute particles and the solvent particles interact to make that solution, that's called solvolysis. There's a fancy word for you. All right, so let's talk a little bit about that process. Like, why would solutions form in the first place? Like, the only way that this is going to happen is if the solute particles and the solvent particles interact really nicely, right? In terms of a solid like brass or bronze, those particles have to be close enough sizes so that the copper atoms and the tin atoms kind of make a nice distribution. Otherwise, it wouldn't distribute nearly so nicely and make such a uniform product, right? But in liquids, we've talked about this before. It's been a while, but if you will remember, way back to our lecture on covalent compounds and ionic compounds, we talked about intermolecular forces. Do you guys remember these? If you don't, and actually I think we just kind of did a shout out to them, I think with gases, very briefly, right? But we said, look, we've got ionic type compounds and we've got covalent type compounds, and ionic type compounds were subject to specifically ion-ion intermolecular forces. This is what keeps that molecule together, is the attraction between the positive ion and the negative ion. And then covalent compounds actually kind of depended on whether you were polar or non-polar, right? And if I am, give myself a little bit more space here, non-polar, if I am non-polar, then what kind of intermolecular forces am I subject to? London dispersion. Good. Excellent. Right. All right. And if I was polar, I had two options. I could be regular polar, or I could be fancy polar with an H attached directly to a F, O, or an N, in which case, what's fancy polar called? Yeah, that's hydrogen bonding. Oh, you were on it already, Erica. Great. Yep, this gives you hydrogen bonding. And if you're regular polar, then you're subject to just dipole-dipole. Yeah, perfect. All right. And then kind of describing what's happening here helped us understand the physical properties that arose from these, right? So I'm making a table, but I don't have any headers here. I ought to move this down. We're going to say, all right, type of compound. And then here we've got our intermolecular forces. And then we're going to have physical properties which arise from these intermolecular forces. And so we found that ionic compounds, for instance, had very high melting points, boiling points, right? Because they were very strongly attracted to one another, and that they were brittle because they have this lattice network of plus and minus charges that could get misaligned and pop apart. And that if they dissolve, that they sometimes dissolve in water. And if they do, they make electrolytes because the individual ions separate. So soluble in water because you have the positives and the negatives, right? And because water in particular, our classic example of hydrogen bonding, has a strong partial negative on my oxygen and a strong partial positive on the hydrogen. And so the charges still attract one another. The charge on the positive ion here is going to be attracted to the partial charge on the oxygen atom here. Do you guys remember this? The polar also had partial positives and partial negatives that would also be attracted to the hydrogen bonding. And the London dispersion has no charges, no partial charges, no full charges, nothing that would make it attracted to the water at all. And so as a result, we see the ionic compounds are soluble in water, and polar and hydrogen bonding. These are all going to be soluble in water, just speaking to our solutions in solubility. But that our London dispersion would be insoluble in water. Or in particular, they would be more soluble in a non-polar solvent. Like oil, exactly like oil, Erica. That's a perfect example, right? So vinegar is a water-based solution, and oil is obviously oil, and they are not soluble with each other because oil is non-polar and water is highly polar. And so you might hear the words hydrophilic and hydrophobic. These are, from these, I think, Greek endings, water-loving and water-fearing. Obviously, it's not that the oil fears the water, it's just that there's nothing attracting the two. And so when a water molecule encounters a fat molecule, it's not really attracted to it. If it sees other water molecules, it's like, hey, I'm going to go hang out with my buddies. And the fat particles just get excluded because they're just not attracted, right? And we had this example of, like, if I had a jar and I filled it with marbles and magnets, right? I've done this, right? So you get a couple of really strong magnets and you have to separate them so that they don't automatically come together. And then you separate them with marbles, right? We have a bunch of marbles here. And then you might put in a couple more magnets. Be really careful so that they don't attract one another. And you continue this and so on and so forth. And then when you're done kind of stacking them carefully, if you swirl this around this jar full of marbles and magnets, what's going to happen? The magnets will attract one another. That's exactly right, Erica. The magnets attract one another and the marbles just kind of make way for them. And what you're going to get is basically a big clump of magnets in the middle and the marbles all around it. And that's just kind of simulates exactly what happens with the water and the oil, right? They just clump together in that situation. All right, so this is kind of the why. Why would solutions even form in the first place? Well, this is why. It's because their particles are attracted to one another. We've talked about this. And so that is actually our first section of the worksheet here. I'm just gonna bring this over here. It's just a review, but at the same time, I do find that sometimes y'all forget what it was that we did. And so it's helpful to be, what's the word? I think it's helpful to be, it's helpful to be deliberate and say, I know that you already know this, but we're going to practice it again because we're going to need to understand what's going on here. So, which of the following atoms or molecules will be more likely to form a solution with water versus with C8H18, right? So water was given here because it is a polar hydrogen bonding thing. So you could kind of easily say, all right, well, any of these ones is going to be soluble in water because of charges. And CH18 is used as our nonpolar molecule here. As you can kind of see if you look at that, carbon-carbon bonds will not be polar. Carbon-hydrogen bonds have such a small electronegativity difference that they're not polar. So really what I'm saying, which of these is soluble in a polar solvent and which is soluble in a non-polar solvent. And you just have to go through this list and say, okay, is this polar? Is it ionic? Is it non-polar? Is it what? And some of these you can tell at a glance, and some of these you're going to have to do math for. So that's okay. We can do this. Let's go through these and see what we can predict. So for C3H8, what do you guys think? Okay. Nicole says, and Erica says it'll go with the C8H18. You know, without even kind of picking it apart, you can kind of say it looks a little bit, structurally, it looks kind of like the C8H18. It has all the same types of atoms. So you can predict that it'll be the same, but you could also pick it apart and say, okay, well, the carbon-carbon bonds will not be polar. The difference in electronegativity values between the carbon and hydrogen bonds is not large enough to be polar, so that is a non-polar molecule. So therefore, it will go to CH18. Good. What about KCl? All right, Sarah says that's going to go to water. How do you know? It's ionic. How could you tell just by looking at it, Sarah, that it was ionic? What are you looking for there? You guys are exactly right. The K is the element potassium. Potassium's a metal. So a metal with a nonmetal or a metal with a polyatomic, basically a metal that's involved in a bond here, you're going to automatically say that's ionic. So because it's ionic, it goes straight to water. Didn't have to draw it out or anything. You're totally fine, Sarah. You're totally good. Okay, CH2Cl2, where is that going to go? Nicole says this one is tricky because it has polar and nonpolar bonds. And Erica gives a tentative classification of C8H18. I'm so glad that you guys recognize that this one is tricky. And it is, yeah, it is. Okay, so here you see, because there's a possibility of the polar bonds, we should probably draw it out. We shouldn't just guess, right? And we can say, all right, so my Lewis dot structure, if I've got 4 electrons from the carbon, plus 1 times 2 from the hydrogen, plus 2 times 7 from the chlorine, gives me a total of 20 electrons. Okay, so we've got carbon has 2 bonds to hydrogen, 2 bonds to chlorine, and that uses up 8 electrons, and then the hydrogens don't want any more, so we can put the rest of these on the chlorine. And when I put 6 on each of those 2 chlorines, that's 12 electrons. So 8 plus 12 is 20. I've used up all of the electrons. And then if we draw this in the correct shape, because there are 4, it's going to be in this tetrahedral shape. Do you guys think we'd never have to do this again? You are wrong. Oh, I'm going to put the hydrogen there. 2 hydrogens, 2 chlorines. Okay, so are the carbon-hydrogen bonds polar? The carbon-hydrogen bonds are not polar, right? Carbon's 2.0, no, 2.5. Wow, carbon's 2.5, hydrogen is 2.1, difference of 0.4. You guys kind of, you didn't have to memorize it, but you kind of memorized that that's not polar. But the carbon-chlorine, because carbon is 2.5 and chlorine is 3.0, it's a difference of 0.5. So that's technically polar. I say technically because remember 0.5 is like our cutoff. So, and remember that it's a spectrum. So it's like ever so slightly, maybe barely polar is what you're going to expect for the CH2Cl2. Now, I'm not going to test you on ever so slightly, maybe barely. You know me. I'm tricky, but I'm not that kind of tricky, right? I'm not going to test you on fringe cases like that. I'm just going to use these as illustrative principles while we're talking, but I would test you on something very clear like KCl, all right? But this one, as it turns out, you might say, well, water, because it does appear to be polar. And you might say, well, CH18, because it actually kind of looks a little bit more like that, and it's only like even barely polar. As it turns out, if you go do this in the lab and try it out, and I have because I was curious, you'll find that it is a little bit soluble in water. You can get, a small amount in there, a couple percent, but it's actually quite soluble in the CH18 because it's just because water is so highly polar and it's a spectrum. Does that make sense to you guys? On the worksheet, if I ever had you turn it in, which of course I never do, I would give you full credit for either answer, H2O or CH18 on this one, because you can make an argument for either one. And really that's kind of one where you just have to go in the lab to just double check, because your prediction, I think, is just based on the principles that we know so far, could go either way. All right. For some reason, when I made this worksheet, I was like, I'll put in some metal atoms and see what you guys do with them. What would you predict? Just kind of iron. If I dumped a chunk of iron in water and I dumped a chunk of iron in CH18, would you expect to see iron atoms floating around in the water, the CH18? Make it a solution. Yeah, not really. It's just going to sit on the bottom. This was me being tricky and being like, would they recognize that some things just aren't soluble in either? They're just going to stay by themselves. I would never put that on the test either. All right, let's look at this one. NH4NO3. What's your prediction here? Water. Why water? Because this is ionic. Oh, good eyeballs. You always have to remember your ammonium polyatomic ion. That's your nitrate polyatomic ion. Because you've got two polyatomic ions together, that's an ionic compound. Good. What about this guy? I'm seeing more question marks. Okay, oh, tricky. Let's draw it out really quickly just to see what we can see. So you've got the carbons on each side and an oxygen in the middle. All right, so this is what this guy looks like. And you guys already know the carbon-hydrogen bonds are not polar. So I've got a little nonpolar cluster on the left-hand side, a little nonpolar cluster on the right-hand side. But because this has 4 electron sets, right? The oxygen in the middle has 2 lone pairs and 2 single bonds. That means that it is bent, right? So we've got the CH3 up here and the CH3 down here. A little bit clearer. And the CO bonds are polar, right? Oxygen is 3.5 and carbon is 2.5. So we have a little polarity going on between the C's and the O's. And it's not fringe like it was here, like the CCl was a difference of 0.5. Like that was just really kind of not enough to get us there. But a difference of 1.0 is a little bit big enough. Yeah, it is, these bonds are polar. So the whole molecule does have a little spot of polarity in the middle. And it is enough to make it soluble in water. Yeah, that's going to go into water. Now again, this is a little bit tricky because I'll tell you what, if you put more carbons, one more carbon on either side, right? The more carbons you add, your balance shifts or tilts, right? From being, having a polar nexus and some nonpolar sides to having a little polar spot and like a lot of nonpolarness. Does that make sense? So if you put 2 more carbons on there, it's going to be a lot less soluble than it is now. But for a very small molecule that just has 2 carbons to start with, that one is polar. And this is the kind of thing that we see in biological molecules, right? Your body takes advantage of these properties to do fun things, like for instance, make a cell using a lipid bilayer that has these nonpolar tails of carbons and hydrogens, and then having the heads be ionic. So they would be highly polar. Does that make sense? Okay, let's see here. How would you predict for NH3? All right, why do you say water, Erica? It's not ion-ion. So it's nitrogen and hydrogen. Yeah, it looks like it can do, Nicole's right, it looks like it can do hydrogen bonding, but you should double check to make sure it is actually polar. It does have the N bonded to the H, but you want to make sure that it doesn't cancel. But if you draw this out, you'll see you end up with, and I'll just gotta do a shortcut and do the work for you here. You have 3 hydrogens and a lone pair, and that makes it polar, right? Because it adopts that pyramidal structure. So that one does hydrogen bonding. It's ammonia. Yeah, dissolves great in water. You could buy that at the grocery store. Ammonia, great cleaning solution, right? Just don't mix it with bleach or you'll die. Sarah, I'm not sure what you're saying, but I'm going to take a guess. So this is not the ammonium polyatomic ion, which is it has a formula of NH4 and a plus charge, because it just has NH3, and you see there's no charge here. So this is not an ion itself. It's not an ionic compound, because as you're saying, if it was a single ion, it like wouldn't exist by itself. You'd have to have another ion with it, right? So the fact that there's no charge there and there's not another ion paired with it, that tells you that this isn't really a polyatomic ion. It's just a covalent compound. So then we follow the rules of putting that together. Does that address what you were trying to say, Sarah? Oh, okay. Okay, sorry. I should probably read the chat a little bit more carefully. Okay. Yeah, that's exactly right. Okay, so, all right, next, oxygen. What would you expect for oxygen? I did say earlier that you can get oxygen in water, and obviously if you don't have any oxygen in the water, then the fish can't get the oxygen out of the water with their gills. And so fish would die if oxygen didn't go into water. But according to what we're looking at here, I mean, would you predict oxygen is subject to London dispersion forces, or that it would be polar? Yeah, Nicole's totally right. Oxygen is nonpolar. The OO bond does not, the electron negativity is going to cancel. So this is a nonpolar molecule. And so we say will be more likely to, or might develop a higher concentration. You're actually going to predict that this would go into the C8H18. Okay, now that doesn't mean that there's none that goes into water, just that given a choice, or if you have, a bowl of water and a bowl of C8H18 and you like bubble oxygen through them, you'll see more oxygen staying in solution in the C8H18 than you would in the water. Does that make sense? It's not like you'll never get any in the water. It's just you'll get more in the C8H18 because it is nonpolar. We'll predict that. Now this brings me, before we continue, yeah, Sarah, it's tricky. You picked the best. Yeah, it's true. They're tricky. One thing about this is that oxygen is a gas, and there is actually a law about this. And so let's take a minute to talk about that. It's Henry's law governs the solubility of a gas in solution. And there's interesting thing happen when you put a gas in solution as opposed to like a solid. So for instance, a solid like sodium chloride, when you put it in solution, you can dump a bunch in, but at a point it gets saturated. You can't put any more in, right? And it'll start falling to the bottom of the solution. Well, if you heat it up, then you can fit more salt particles in there, right? So you can make it saturated, you can heat it up, and then you can add more. I think most people understand that generally speaking, solubility will increase with increasing temperature, right? You can get more sugar to dissolve in the water. You can get more salt to dissolve in the water at higher temperatures. But the opposite is true for gases, because gases already have a lot of movement energy and they want to be zipping around, and the higher temperatures you give them, the faster they're going to escape that solution. Does that make sense? This is why, for instance, if you open up a soda, you have like an open can of soda, or maybe a one that you've got, it's from the one that you got from Sips or Fizz or something that's got like the plastic lid. If you store it in a hot car versus if you store it in a cold refrigerator, you'll find that it goes flat a lot faster in the warmer environment because the gas escapes the solution. Does that make sense? Oh, I'll get back to you, Dave. But yeah, that's why it goes flatter faster, because with increasing temperature, it actually becomes less soluble. But Henry's law basically says, look, if you want a gas to dissolve in a solution, what we find is that the solubility of the gas in solution is directly proportional to the pressure of the gas on the solution. So in terms of fishies and water, we have here's our ocean, and here's our atmosphere, which is 21% oxygen, right? We have little oxygen particles, 21%. At atmospheric pressure of 1 atmosphere, that means 21% of the atmospheric pressure is pressure of oxygen particles, which are zipping around, and they're also bouncing off of and sometimes being absorbed by the water, right? So the water can release oxygen, the water can absorb oxygen. So long as there's a substantial amount of oxygen sitting on the surface of the water, well, it doesn't have to be pure oxygen, it can be just a partial pressure, then some of it will be absorbed by the water. And if you keep a fish tank, then you'll also find that having water movement helps a lot, right? So you might put a bubbler in there. That'll also help. Does that make sense? All right. Now, to take this another step further, just to talk about this with carbon dioxide. So if you have a soda and it goes flat, the reason is when you opened it up, let me get a cola here. Here's our solution, our cola solution. When you opened it up, oh geez, this is a terrible picture. Okay, we'll make it here's our cola bottle. Then the carbon dioxide particles that were dissolved begin to escape. And the pressure of carbon dioxide on the surface is very low because the amount of carbon dioxide in the air is less than like 1/3 of 1%, right? So your equilibrium of carbon dioxide gas escaping and carbon dioxide going back in under those conditions, eventually all the carbon dioxide is going to escape. There'll be a very tiny amount of carbon dioxide in the solution. Does that make sense? Again, keeping it cold can prevent that escape. And keeping it pressurized, right? So if you put the lid back on, then some will still escape until you get lots of carbon dioxide in the air above it, but then it provides enough pressure that it puts it back in, right? So keeping a tight lid on it will help. Alternatively, if all of it has escaped, then you have to directly put pressure in there. And that is the idea behind, for instance, oh gosh, now the name escapes my mind because it's morning time. But you can buy these things at like Bed Bath & Beyond and little carbon dioxide cartridges and like make your own sodas, because it will pressurize the system with carbon dioxide. Soda stream, that's what it's called. You guys seen those things? If you like really love soda, but maybe you don't like all of the junk that's in them, you're like, what if I just took like apple juice and stuck carbon dioxide in it, then I would feel like I was drinking a soda, but it would just be natural apple juice, right? Be great. That'd be kind of fun. But you can get the same effect with a pressurized system and another source of carbon dioxide, such as Zach mentions a keg, right? So a keg might be welded so that it can withstand great pressures. And then on the inside of that keg, if you're my uncle, you're going to stick root beer stuff and then a bunch of dry ice and then seal it up. Now, I don't recommend that you do this, actually, because sealing dry ice in a container is a great way to make a bomb. So it would have to be like an actually like well-constructed keg, or else somebody's going to die and I'm going to get in trouble. So don't do this. But that's one way to do it, is to put dry ice in it, and that will produce carbon dioxide. The traditional way is to ferment it, and then the yeast produces carbon dioxide because it's undergoing respiration, as all biological creatures do. And the carbon dioxide that it releases gets absorbed as carbonation. Does that make sense? Okay. At the end of this lecture, I do have, there's a little story, and I'll just tell it to you here because I think it's funny. But when I was a kid, we were going to go on a car trip, and my dad, who was a chemist, was like, I know, I'll use dry ice in the coolers instead of regular ice, because regular ice melts and gets everything soggy, and we don't like soggy sandwiches, right? And dry ice is going to keep it really cold for like a 12-hour car trip. I think we're going from Utah to Arizona. And like halfway through, I get out and I like eat a peach, and it's the nastiest thing I ever tasted. And of course, we found that as the dry ice sublimed inside of that cooler, that it created a whole atmosphere of carbon dioxide inside the cooler, and everything became carbonated, including the peach. Now, it's a funny story, but it's actually a really great story, because the reason the peach was nasty to me was not because it was carbonated. It's because I wasn't expecting it to be carbonated, right? Have you guys ever gone to like drink water and found that it was Sprite instead once it hit your mouth, and been totally disgusted by that? Or vice versa? The expectation is the key here, right? Because Sprite tastes yummy, and so does water. And if you're expecting water and you get water, it's great. And if you're expecting Sprite and you get Sprite, it's great. But if you're expecting one and you get the other, then your brain rejects it, right? It's like you're expecting water, you get Sprite, you're like, this is bad water, because it's not actually water, right? Your brain like tells you it's nasty. Anyway, so I decided, let's actually try this in an experiment. And it turns out carbonated fruit is delicious, right? It's like soda fruit. It already has the sugar in there, and then you get it carbonated. If you like carbonation, then it's fabulous, right? So I've done this often in class for fun. Grapes do really well because the thick skin, it takes a little bit while to penetrate, but then also they go flat a lot more slowly than, for instance, raspberries do. And they're great. So I recommend this. You guys should try it. Again, you don't want like a well-sealed cooler. Maybe a styrofoam one would be a perfect one, right? Because gas is still going to be able to escape. But you just want to be able to get like a full atmosphere's worth of pressure of the carbon dioxide on top of that. And everything gets carbonated. Carbonated banana, the problem with bananas is that they kind of go brown if they get cold, right? That's why you don't ever store them in the fridge. But you could try it. Clementines are delicious. Grapes are delicious. Strawberries and raspberries and blueberries are great, but they go flat a little bit quickly. But you should know everything gets carbonated, right? So I did this once, going to Lagoon, when you like pack a cooler. The mayo on the sandwiches, carbonated mayonnaise. Not quite expecting that. It was very interesting. It wasn't awful because I knew that something could happen. I was actually wondering if the ham would pick it up, but it was the mayonnaise that picked it up. It's too bad that I can't see your faces, because that's like the best part of this lecture. But if you left a soda or just like a drink open in there, then that drink would also become carbonated. The key to doing this well is to get a good cooler with a lid that isn't going to provide like a hard seal, right? Gas has got to be able to escape. If you're not sure, you could just put the lid on lightly. And then a couple pounds of dry ice on one side, and actually put some water bottles in there as a thermal buffer, because you don't want frozen fruit, you want carbonated fruit. So on this side of it, you're going to put your grapes and your oranges and your bananas for science, right? And your sandwiches, if you're curious what a carbonated mayo tastes like. Whatever you're going to have. It's kind of fun. And then leave it about 24 hours. And then you should post about it on the discussion forums, because it's actually kind of fun to do. To do extra credit on this, just like we did for ice cream, right? Make you guys do that. All right. Okay, that was a really long aside based on our analysis of oxygen here. Whew. Let's finish the rest of these. Oh, Erica has a great question. Where do you even get dry ice? You actually just get it at grocery stores. I can get it. I've got a Dick's Marketplace nearby me. I can get it there. Smith's also will carry it. But they don't, you can't just like pick it up off the shelf, because then irresponsible teenagers, being irresponsible teenagers, go commit felony crimes. Because again, if you put it in a sealed container, it makes a bomb. So you have to ask the person at the checkout, like, hey, can I get some dry ice? And they'll get it for you. It's fun to use for Halloween to make like bubbling cauldrons and stuff. And actually, you can even use dry ice to make homemade ice cream. That sounds interesting, because it freezes it really fast. Part of the best homemade ice cream, you have to freeze it quickly or keep it moving so it doesn't make big ice crystals. So, okay. So gold here, AU, is in the same pot as iron. It's not going to go into either of these solutions. Neither. Good. CH3OH. We've got the CH3, and the CH bonds are not polar, right? But then you have this OH, where the OH bond is polar. And if you draw this out, you'll see that it has 4 electron sets. So it's bent, and 2 of them are lone pairs here. So this one polar, very polar OH bond makes the molecule polar enough that it definitely goes into water. But just like the example above it, if I had like 5 carbons here, that would be too much, right? There's a limit to how many carbons this one OH, we call this an alcohol group in organic chemistry. This alcohol can only carry up to 4 carbons with it into the water phase. And even 4 is a stretch, right? So butanol, which is the alcohol with 4 carbons, has limited solubility in water. But just 1 carbon, we can do that. All right, what about LiI? Water. Why water? Because it's ionic. Excellent, you are on it. All right, lithium is a metal, so you say metal, non-metal, definitely goes into water because it's an ionic type compound. All right, what about SiCl4? Why C8H18, Nicole? Yeah, this is a nonpolar molecule, although you might draw it out because the SiCl bond is actually polar, right? The difference is large enough to be polar, but they all cancel, right? Because you end up with this tetrahedral shape, and all of the negatives are on the outside. So if we drew the Lewis dot structure, we would see that it looks like this. And then of course you draw the Vesper shape, and you still have to remember how to do all of this for this chapter, right? And you're going to be tetrahedral here. Go. So tetrahedral SiCl4. The Si is partially positive, and the Cl is partially negative. So you look at each bond again. So partial positive on the Si, partial negative on the Cl. For this bond, partial positive on the Si, partial negative on the Cl. For this bond, partial positive on the Si, partial negative on the Cl. For this bond, partial positive on the Si, partial negative on the Cl, and then it doesn't pass the line test because all the positives are in the middle. Does that make sense? You had the right answer. I just wanted to make sure everybody understood why that would be the right answer. Good. All right, so this is just trying to explain why do things form solutions in the first place and how do they interact, right? So that's exactly what's happening here. And that is the end of our first lecture here. I hope you have a great day.